Alright, so in this video, I'm going to be going through some of the questions you guys have posed me, um, electronic questions, yeah. So these questions on the screen are what I'm going to go through. Uh, I will not be doing some of them because some of them are dumb questions, but there are some good questions in here, so I will be going through them, yeah. So let's just begin. Okay, first question. How do we know when to use a buzzer or a microphone? What? I mean, yeah, this is we're not starting off strong. This is a stupid question. Because first of all, a buzzer and a microphone do two different things. For starters, a buzzer is an output transducer. A microphone is an input transducer. They're literally two different things. A buzzer makes sound. A microphone detects sound. So how do you not know when to use it differently? If the circuit requires an input of sound, which then you use a microphone, obviously. When you need to output a sound, then you use a buzzer. So the fact that this question was asked means that you don't know the difference between a microphone and a buzzer, which is very concerning because if I just leave my house right now, I go to the street, I ask the first guy, hey, what's the difference between a buzzer and a microphone? They will definitely know the answer. Okay? So the fact that you ask this question is really mind-boggling. So let's just move on. Okay. Um test. Yep, okay. So next question. What component do I think is coming out? For example, the pin connection diagram for the 74LS390 IC, which was worth 6 marks in a 2023 paper. And how do we draw it? Okay, I don't actually officially have um uh what uh what do you say? Wait, what's the word like of a prediction? Yeah, I don't really have a prediction, but if I were to guess, I would say it's probably still going to be the 74LS390. It probably will be. How do we draw it? Okay, so the 74LS390 is the decade counter, right? How you draw it is just remember that your pin on top here. Okay, yeah, just remember that the pins that you need VCC and you need ground, and it's always like this. Then you will have your clear signal, you have your clear, you will have your clock, which is like CKA. I think it's something like this, yeah. Then you will have A, then you will have like another A, B, C, and D. 1 2 3 4 1 2, yeah, and then like these two are always connected when you're doing intercade counter. Then for this side you're gonna do the same thing again. Then it's literally clear the CKB. Then this will now be QB. This will be, it's the same, A B C D again. It's and the reason why I can immediately say like this is because I know all the pins and I know what's the output of the thing, of the decade counter, which is 4 bits, and I know what the pins do. Okay. um and this is pin 1, this pin 1, and then wait, why did I write it upside down? This pin 1, this is pin 16. So okay, and then let me just talk about the 74LS390 more bit. You should know that A is always the least significant bit, D is the most significant bit, and then clear clear will always clear the count for that specific counter. Oh, the 390 has two counters, by the way. This side counts for this one, this side counts for this one. And then if you clear here, this will clear this one. If you clear here, this will clear this one. And for clear, it activates the clear on a rising edge. On a rising edge. Then this is the clock. the clock, right, will advance or increase the count of the specific counter. So this clock will advance this count, okay? And for the clock, the clock only triggers on a falling edge. So yeah, so this is the 390. Okay, so that's this question done. Okay, how do we know which specific components to use in drawing our circuits? I feel like this question has some like like you did a question in a paper, right? Then you're like, oh, what do I do here? Then after you ask this. So, but it's kind of hard for me to answer this one because I don't have enough context, I think. Because to me, this looks like a dumb question. It's like, how do I know? Okay, let's say you're running away from a wolf, okay, in the forest. Then suddenly you come across a river. The only way to pass the river is by swimming through. Then I'm there with you. Then you look at me and you ask me, what do I do now? It's like that. This question you just asked me is like this. Obviously, you have to swim because based on the context, you're running away from the wolf. There's a river. You have to pass the river. You have to swim. So, how do you know which specific components to use? It depends on the context. Yeah, if you provided me the context that would show ambiguity in what component to use, that would be helpful. Okay. If not, then I'm done with that question. How do we tackle to solve the graph questions, the op-amp, diodes, and rectifiers? Um, okay, graph questions mean many things, and then you provided me three examples of those many things, so I guess I'll go through all three. So let's start with op-amps. Okay, op-amps, you got your inverting, your non-inverting. Usually, and then if they give you a graph, it'll probably be like this. Like they'll say, okay, with an AC signal input with like this, this is time, this is voltage. Then peak to peak like 4 volts, I guess. So 2 and 2. Okay. One period is I don't know 10 milliseconds. Okay. They ask you maybe okay, then now this signal goes through inverting amplifier. Okay, so inverting amplifier, it looks like this will be V in, then you ground the positive pin, then your output, and it's connected to another resistor. Then for this kind of graph question, they might ask you um, calculate or draw the output waveform from the op amp. I'm going to assume this is what you're asking. So for this specific example, okay, I can't get the okay, alright. For this specific example, you just need to know you need to know how to get the output of. Oh, I'm lagging. Oh my gosh, I need to get a new computer, bro. Okay, I don't know if anything I just recorded was being said. Let me show my OBS for a second. Test. Okay, hopefully it's fine. So you need to know the how to get the gain of this op amp. So it's inverting, right? You need to know the formula, the gain, which is ACL, I think. I'm not really sure. I'm very agak-agak one, okay? So you need to know that this is equals to negative RF divided by R in. How to remember this formula? It's inverting, so there's a minus, and then fin. Fin, like the guy from Adventure Time. Or you can think of fin as like the fin of a shark. Okay? So then let's say, okay, they give you this is 1 kilo ohm, this is 10 kilo ohms. So if you calculate this, right? So 1 kilo ohm, so 1 kilo ohm divided by, so this is 10. So the gain is 10, or negative 10 rather. So now you need to know that the output, let's say the peak voltage is 2. The new peak voltage will be 2 times ACL, and then this will be negative 20. So now you know that the new waveform, when the input is at 2, the new waveform will be at negative 20. Then you do the same, you can do the same for the lowest peak if you want, but for me, I don't really need it. Then from this, you can actually find that the new waveform will be like this. Okay, crap. And then peak to peak is 40 volts lah. So this is how to do an op-amp question. I didn't really explain it very well, so if you have further questions on how to do op-amp, you can ask me later. I'm doing a live lesson later, I think. Okay, wait. Why am I? Alright. But anyway, I think there's a question later on about op-amps here, so I'll talk about it later. Diodes. Okay, diodes they will they'll probably give you a graph, or oh okay, a different type of diode question is like they might draw you a diode, then they give you a graph, right, of like it's like voltage, it's like current against voltage. Wait. Let me fact check myself. Give me a second. Oh my gosh, I'm lagging. Yeah. Okay. So they might give you this, then they say, oh, okay, this is a practical diode, then draw the graph. So to tackle this kind of graph question, it's just memorization. You just need to know. You just need to know that the waveform, or you just need to know that the graph is going to look like this. You need to know that this is the knee voltage. You need to know that this is the breakdown voltage. You just need to know. So that's how you do diodes, okay? Next. And then rectifiers. Rectifiers, I'm going to assume you're talking about AC rectifiers to rectify into DC current. And I'm gonna okay, and I'll talk about both half wave and full wave. So for half wave, your graph is gonna be V against time. If let's say your input, let's say it was like this, okay, then your output is going to be like this, okay. And notice how okay, one thing to note here is that let's say the input peak voltage was like 9 your output peak voltage is going to be 9 minus the breakdown voltage of one diode, okay. It's just, and this is because of the way the half wave rectifier circuit is, because it looks like this, right? Then your AC is through here. It has to go through a diode once, and the diode has to eat up some voltage to be in operation. So that's why it will go down by one. So this is for half wave. For full wave, it is kind of the same. For full wave, you got your waveform here, right? Then what's gonna happen is it's gonna be like this. Okay. Oh yeah, and one thing to note, right, is the waveforms do not touch each other. Because again, everything is shifted down because of the breakdown voltage of the diodes. Okay. So now the new peak to peak voltage is minus two breakdown two forward voltage of two diodes, because um if you watch my if okay, because to rectify the DC into AC the signal has to go through two diodes at all times, okay. You can, and that's all I'm going to say for this. You can see this properly if you watch my full bridge rectifier or my rectifier videos, okay. Okay, anyway, um wait, how do I, okay, how do we effectively use the op-amp formulas, because I'm still a bit unfamiliar. Okay, so for this I'm just going to go through op-amps again. However, I highly recommend you watch the op-amp video that I have, because that one is going to give a better explanation than the way I'm going to explain now. So the formulas for op-amps, you only have two. Okay, the formulas for op-amps, there's three kind of. There is one that will give the output of the op-amp. So you have your op-amp, right? Then you have your input and your output, and you have your two inputs, which is like V in plus, okay, wait, V plus, V minus, and you have your output or V out. There's actually a formula to get V out, which is the V out is equals to open loop gain multiplied by V plus minus V minus. So basically, the open loop gain of an op-amp is just a property that an op-amp has. Um, in an ideal setting, the gain, the open loop gain is infinite. Okay, but in practical settings, the gain is probably like a very very high number lah. The gain is like in the millions, I think, or in the hundred thousands. Okay, just think of it as a constant that you're multiplying. So this is one equation. Do note, if your output is like negative 69 billion or whatever, don't forget that for op amps, the output is always clamped by the bounds that you give. These things are bounds, and then if it is negative 69,000, it will be clamped to 0 volts. Oh my gosh, I'm lagging. 0 volts because you're giving it 0 volts as the bottom bound. Okay, so this is one equation. The other equation you need to know is um, for inverting and non-inverting amplifiers. Okay, for these, you need to know that an op-amp can actually amplify AC signals. So, and they can do this in two different configurations. So, the one that I talked about just now is the inverting amplifier. And then the configuration looks like this. I'm lagging again. Oh my gosh, I'm lagging so badly. Okay, one of the configuration looks like this, and then this is grounded. This is R in. It's called R in because the resistor is always at V in, and then this is R F. F stands for feedback. This is called a feedback resistor. Okay, and then we also have the non-inverting. So for non-inverting, we actually going to the resistors for the resistor configuration for inverting and non-inverting is always the same. Okay, I'm lagging again. Oh my gosh, I'm lagging so much. Okay, so the resistors always remain the same. Then for non-inverting, you ground this one, then this is your V in. So the formulas for these two calculate the gain or how much your AC signal is going to be amplified. And the formulas for both are different. For inverting, I'm lagging again. Oh my gosh. For your gain, it's gonna be equals to negative RF divided by R in, as I said just now. So for this, I'm lagging so much. For this, you can try to remember it as it's negative because this is inverting, and then RF in fin. Okay. Then for non-inverting, it's 1 plus RF divided by R in. Okay, and then you can think of this as it's because it's non-inverting, so it's like positive. Okay, it's not really like that, but it's just a way to remember. Okay, how do we use the equations effectively? To use them effectively, you have to know them. So basically, this is telling me that you don't know this lah. So again, to calculate gain, I think I say this I say this wrongly in my video, but basically, both of these equations will give you gain. They'll give you gain, right, in the end. To amplify, to get your output, okay, let's say your input peak to peak AC waveform is 2 volts, okay. If you want to get the new peak to peak voltage, you take the old peak to peak voltage times ACL, or times the new gain, the gain that you get, okay. So that's how you use the equation, because I don't really know what you mean by effectively. So I just re-explained the entire thing. Okay, I'm just gonna delete this. Alright, next. Okay, wait, let me. When they ask you to for a block diagram, what must we write in our block diagrams for the marks? This is very context based. So the textbook has a few examples, like in the first few pages. Like for one, right, they just have something like this. Okay, for this you need to know that there are three stages in like any circuit. There is the input stage, there is the process stage, and there's the output stage. Okay, so a simple example would be like button, not gate, LED. Okay, that's a simple example. The textbook also gives another way of drawing this. They give it like this. They write input, they write process, then they write output. And then what they do is they block out, not block out as in like they don't let you see, they like draw blocks for the input. So for this I'll do like, I don't know, button, switch. Then the process can be like, I don't know, logic system. Okay, then you draw arrows. Then the output, it can be multiple things basically in this different way. I don't know, LED, buzzer. Okay, but this is not your question. Your question was, how do I get the marks? What do you need to write? You need to write input, process, output. Definitely you must have. You definitely need to draw arrows. Arrows is an important part because that shows the flow of the circuit. And then lastly, right, you need to write out the actual button, switch, logic system, and whatnot. So for one of those marks, it is context based. But for two of the marks, definitely how to get, you need to write input, process, output, and then you need to draw the arrows and the blocks. Okay, that's my take on this. Okay, next question. Do we need to know different types of resistors? Carbon, e.g. carbon resistors. What if it's before they introduce to us the components? Did I say did I say anything about components? I said you need context. Did I say anything about components? You don't. What if it's before systems? Then you read ahead. No lah. Once you don't see, then you kill yourself because you don't know how to answer. Then you just kill yourself, right? Yeah. No what are you saying? Do we need okay? Because it's in the textbook. Because it's in the textbook. Yes, you need to know. Like carbon resistors, wire wound resistors. I think you only need to know carbon and wire wound crap because I remember in the textbook that they specifically give a table to show the advantages of using wire wound and carbon resistors and the disadvantages. So do you need to know? I suppose so. Um, Specifically go ahead and read on wire wound and carbon film resistors. And then you specifically should know the advantages and disadvantages of using them. Okay. What other thing would we need to know about CMOS and TTL other than just the advantages and disadvantages? Okay, there's like two things you need to know. The first thing is the difference in input and output voltages for CMOS and TTL. Okay, so what do I mean by that? Basically, for a TTL chip, for your input voltages, uh, there's input voltages, right? It's either logic 0 or logic 1, right? Okay. Basically, the input will have a tolerance. So you need to know, okay, I don't know if you need to know the exact value of the tolerance, but you need to know that there is a tolerance. So for the input, it's around, just imagine the range of voltages as a bar here. So logic 1 will be like from 3.5 volts to 5 volts or beyond or whatever. What? Okay, alright. So, and then, oh crap. And then logic 0 will be from some value which I don't remember to 0 volts. Okay, you need to know this. And then you need to know the output as well. The output is also from a range of values. Okay, and then you need to know the distinction between this and CMOS. For CMOS, the input range I think is similar-ish, but the output is very very 准 one. The logic 0 tolerance is very very small, and then, or accurate, yeah. And the logic 0 tolerance is very very small. Logic 1 tolerance is very very high, very very small. So you need to know this, and then you need to know that the output for a TTL chip is something called open collector output. So what does this mean? Let's say let me just, okay, I'm teaching something new here. I'm going to teach you about the open collector output system. So let's say we have a NOT gate. Let's say I have a NOT gate here. Oh my gosh, I have a NOT gate. So we have an input and an output, very very simple. And then let's say this is a TTL chip. What a TTL does with the output here is it feeds it into a not resistor, into a BJT, and then this is the new output. This is the new output. Why is there a 0 here? Right, this is the new output. So what's the difference of having this thing and not having this thing? This it basically, the output is different now. With the BJT system here, if this is high, then current can flow through. If this is low, current cannot flow through. Basically, the logic system here controls whether the current can flow here or not, or controls whether the resistance is very very high or very very low. So for TTL chips, this is why you need a pull-up resistor, okay? Because the output of the TTL chip is not logic 1 or logic 0 necessarily. It can maybe be very very high resistance, very very low resistance. So now as the engineer, if you want to produce a logic 1 when this is 1, so let's pose a case, okay? When this is logic 1 output, the current will flow. But now, how do you get an actual like 5 volts or whatever? Okay, what you can do is you can create a pull-up resistor at 5 volts. What this will do is when the current is flowing, like this, it will force 5 volts to be pulled down here and then be spread across this node. And then what this does is that it will hey, wait a second. When this is 1, this will allow the current to be 0 volts. This will make this 0 volts. As such, the voltage here will just flow like this, and it will not go through here, because here is definitely the resistance is higher. So when this is 1, the current will actually only flow through here. So this is one case. The other case is, what if this is 0? Then the current here cannot flow. So the current now has to flow through this way. Okay, and this is the open collector output system. The reason why it's called collector is because this is the collector pin of the BJT. Okay, Nikki, what's the point of this output system? Okay, and I'll show you now. Where's the CMOS detail stuff? Did I delete it? I do not remember, bro. Okay, basically for okay, I did not want to do that. Basically for CMOS chips, your input and output, as I showed just now, is like the range is 5 volts, 0 volt. But you can actually make it as an engineer to 10 volts, 0 volts. Okay? You can do this for specific reasons, like if you want to drive something or whatever. Basically, there are reasons to do this. And this is where the TTL open collector output may be helpful. Because now, what if, let's say I have this, and then um, I have this lah or whatever. Okay, now what if this is TTL? What if this is CMOS? We know that the TTL output is 5 volts as we saw just now. Okay, but the input of the CMOS now, if it's in this 10 volt thing, what if the tolerance, what if 5 volts is here? So this is not logic 1, this is not logic 0. So now this TTL cannot communicate to this CMOS. So what can we do? We know that the output of a TTL is using a open collector system, and now and we know like this is 5 volts or whatever, right? But we need 10 volt output here. So how do we do that? Because this is an open collector output system, we can use the pull-up resistor again, and we can actually make this into 10 volts. And this will make it such that when it's logic 1, the output will be 10 volts, not 5 volts. And that's why this is important. So now, all we need to do is we add a resistor and then 10 volts. And we're done. Okay? And this is a subtopic in CMOS and TTL, which is about interfacing a CMOS to a TTL and whatnot. Okay, so this is how to interface a TTL into a CMOS, but what about interfacing a CMOS into a TTL? Okay, so now let's say this is TTL. Let's say this, let's say this is CMOS, this is TTL. So do we need to change anything for CMOS into TTL? Yes. This is one more thing you need to know. The output of a CMOS, the current is usually very, very low. So, and this current is so low that it may actually affect the input into the TTL, as in like it may not be enough. So what you need to do is you need to use something called a CMOS buffer, which will help not really amplify or but help tune the current into the TTL. Okay, why am I saying all of this very, very briefly? I don't think you're gonna need to know this in depth. Okay, this is why I don't even have a video on CMOS and TTL. But if you want to know more, just read the textbook. Honestly, I would not have to do this at all if you guys just read the textbook. But here we are. So just do me this one favor. If you want to read more about this, which I wouldn't say is necessary but encouraged, then just read the textbook on this chapter. It's like um it's 300 page 300 ish. Okay, but this is what the other things that you need to know for CMOS and TTL. Okay, I don't quite understand debounce switch or contact bounce. Can help me to further explain. So I'm gonna assume that you didn't watch my video where I explained contact bounce. If you have, then I don't know, because that's quite a good explanation on my part already. Okay, for this explanation, for those the viewer, right, I'm going to be using my camera. Okay, so I'm gonna be explaining. Wait, let me see if OBS can see this. Yeah, okay. So I'm gonna be explaining contact bounce using physical means. So what is contact bounce? Let's say we have a mechanical switch, and then we press it down. If we look at the output and then let's say the switch will allow current to flow, whatever. If we look at the output of this switch in an oscilloscope and we really zoom in, we might not see an immediate jump. What we might see is a little bounce and then a normal. Why is this so? It is because of the way a mechanical switch works. So let's say this let's say this table is the output of the switch, and let's say this is the input. To close this circuit, I can connect this marker to the table, and then what this does is it allows current to flow from the input, which is the marker, into the output, which is the table. So this is pretty much a switch. I can control how the current flows through this switch mechanically with the use of putting this marker against the table and then releasing it from the table. Here's what happens when I do this, okay? I don't know if you guys can see this, but basically, when I do the action of closing this, there is a bounce. There's a bounce. Like that. I can actually do this. Oh, I'm lagging. Oh my gosh, I'm lagging. Okay, look. Look. You hear that? And I'm not even forcing it to do this. I'm just hitting it. Basically, okay. Basically, you can hear the bounce. So this happens at that small level in every mechanical switch. It will happen. So that's what contact bounce is. And then when it bounces, it closes and opens the circuit very rapidly. Very, very rapidly. So it became on off, on off, on off, on off, on off very, very rapidly until it reaches a stable state when it finally closes. So that is what contact bounce is, okay? If you have any questions about that, because this explanation is the exact same explanation I did in when I was going through some papers. So if you still don't understand, I can try to help you further. But that's my explanation to the general explanation lah. So that's that. Okay, capacitor charge discharge time. I'm not gonna go through this because this is literally I have a video on this. Okay, but this I will go through. How is a resistor and capacitor become a timer? Okay, so I can understand where the confusion comes from here because all you're doing, right, in an RC circuit is you're just connecting a resistor to a capacitor, and then yeah, it takes time for the capacitor to charge and discharge. So what? How does this actually control time? Okay, for this I will give you a circuit that can possibly um be like a timer. So let's say I have this RC circuit, and then now let's say I have a voltage comparator. Okay, and then let's say there's like this. So now and then let's say there's a switch or whatever. Okay, so if and then you need to know the charging diagram, charging graph of a RC circuit. It's gonna look like this. And then we know that at 5 tau, it's gonna be 99.3% of the applied voltage. So what we can do is that we can set the voltage here to be the same as here, 5 volts. It is 5 volts lah, because the applied voltage is 5 volts. Or we can set it to be here, which might be 4.7 volts or whatever. So we know that the capacitor is going to take time to reach this value. It's going to take some time. And okay, let's say this is just 1 tau lah. Okay, assume this is 2/3 or whatever, 2/3 the voltage or whatever. So this is pretty much it. This circuit, when you close this it's going to take 1 tau. If this value here is the same as this it will take 1 tau for this output to become high voltage or 5 volts or whatever. Okay, So how does it become a timer? This is one example. This is one example. I hope this answers your question. If not, I can probably think of a different way to explain it. But this is how it kind of works as a timer. Okay. Pins, inputs, and output for IC555 voltage comparator, etc. I'm not answering this because I already have a video on this. 555 wiring, no. I don't know, no. Chapter 15, sure. Capacitor takes time, resistor slows it. Yeah, sure. Oh yeah, and for RC circuit, you can think of what the resistor does as making the capacitor. Okay, we all know that a capacitor takes time to charge and discharge, but a resistor limits current. So if we add a resistor, it actually slows down the charging rate because the current supplied to the capacitor is decreased from the resistor. Okay, so that's that. Chapter 15. And how do we identify the terminals of a microphone? How do we, okay, I'll talk about chapter 15 first. So I also don't have a video on chapter 15 because I don't know, I was kind of lazy, I guess, but I guess I'll just verbally talk about it. So chapter 15 is about the engineering process, and there are like three subtopics in that. It's like how to to plan your time with a Gantt chart or whatever, the different ways of measuring shit with like or different tools you have, and then like communicating or something. And then in all those three, they just talk about how to use a Gantt chart or something, how to use like, oh, what is a power supply, oh, what is a multimeter, oh, what is an oscilloscope do. And then like, oh, for communication, right, it's mainly like in your report, right? Let's say in your report you got like you got a circuit, this is a thyristor, but you don't have to worry about it. So and then let's say this is figure this is figure 6.7, right? Then you can have text on the side that says referencing figure 6.7. This is communication. Okay. So the reason why I didn't have a video on this, right, is because we spent about 2 years in the electronics classes doing practicals. And through these practicals, whether you were paying attention or not, you would have learned what a multimeter does. You would have learned what a power supply does. You have learned this already. You have learned how to put the chip into a breadboard. You know this already. You spent 2 years doing this. So that's why I didn't really talk about it. But chapter 15, I guess the main things you need to know, if they are going to test chapter 15, they'll probably ask you about how does a Gantt chart help you be more efficient, or how do I plan my time properly, and they'll probably specifically ask you about the advantages of using a power supply or the advantages of using batteries. It's very stupid, right? But that's probably what will come out if they test chapter 15. Okay. So okay, how does a Gantt chart help you be more efficient in time? Is because I mean you can say anything okay. Like Gantt chart you have, oh, you need to do A and it's going to take some time. You need to do B, it's going to take some more time. You're going to do C, it's going to take some time. Then as you are doing these things, you will see, oh, A, I actually do like this already. A, I can actually shift this down a bit or whatever, or I can have some tolerance for B. So this allows you to manage your time because now you know how much time you can allot to each task. Okay, so briefly it's like that lah. Okay, again I really don't want to talk about this because it is damn useless. Okay, if the question at max is like 3-ish marks. Okay, then the advantages of a power supply, yeah, 3-4 marks versus batteries. I'll just talk about them, right? Batteries, portable, portable. Batteries cheap. Power supply, oh, not connected to mains. Not connected. Mains is your cha tao, your like your freaking house voltage, or your 235 volts AC 50 hertz. Your power in your house. That's what mains is. Power supply advantages. Socket. Oh yeah, socket. Okay. Power supply advantages. Doesn't run out of battery, so you don't have to replace. Doesn't run out of battery because it's connected to mains. Um, I forgot the others. Like you can change the voltage. You can change the voltage. The current output is higher, and I think that's good enough lah. That's all. You aga, you know this already. You know this already. Just come out of it during the exam. It's fine. Okay. Okay. Last question. How do we identify the terminals of a microphone, and how do we connect it? Okay. For this, you need to know. Okay. What the textbook says is that a microphone. It looks kind of like this. You need to know that the negative pin is connected to the case, and you need to know that positive pin is not connected to the case. Okay, what does this mean? This means that if you were to get a multimeter and if you were to probe like this, and if you were to check the resistance from the negative terminal to the case will be very, very low. Why? Because they are connected together. So there's like very, very little resistance. But now if we were to do the same for this positive pin to the case, the resistance is going to be very, very high. And it'll be high because they're not connected together. Okay? So how do you do it? You take a multimeter, you connect one pin to the case, and then you measure the resistance from negative terminal to the case, positive terminal to the case. When the resistance is lowest, right, that pin is the negative pin. Okay, and how do we connect it? So a microphone will have a positive and negative pin, right? You can connect. How do you connect it? If you're going to connect it to input, right? You can. I don't know. I have no idea. Um, it really depends on context. Let's say you want your microphone to power an LED for some reason. Then I guess when you create a sound, right, a small current will be generated. Then you can connect this to the base of a transistor, or you can use a Darlington pair or whatever. Then you can do a LED, and then this is grounded, of course. And then this LED can also be a buzzer lah. How do you draw a buzzer? It can be a buzzer also. There's negative voltage spike. Um, Technically I guess, but this is a AC system. You don't really need to care. Okay, and then instead of a BGT, you can use a MOSFET lah. Okay, but you guys don't know what MOSFET is. So um, I suppose I'm not really answering this question lah. All right, that's it. Um, I want to keep this video short so you guys can watch it. So okay, I guess that's it lah. Yeah.